So, hello. So, in the strength of material interview preparation part 7, let's discuss about the torsional shear stresses. So, in the given shaft like this, if we create a torsion like this, if we twist the rod like this, so what will be the shear stress induced in the shaft? So, there is the equation for torsion equation, that is T by J, rho by R, G theta by L. So, T is the torsion, J is the polar moment of inertia, rho is the shear stress induced in the torsion, and G is the modulus of rigidity, that is rho by shear stress by shear strain, and theta is the angle of twist, L is the length of the shaft. So when we twist like this, so this is the cross section of the shaft for the given radius R. So this is the shear stress induced in the shaft, which is basically a rectangle. That means over the length of the diameter of the shaft, the shear stress is constant. Okay, so to find the polar moment of inertia, so which is perpendicular to the plane of the section. So for circular section, the formula is pi d power 4 by 32. So for the along this axis, it is pi d power 4 by 64, and along this axis it is same. But along outside, the polar moment of inertia axis is perpendicular to the section, so the axis is outwards. Okay. So if you want to calculate for the hollow sections, the formula is this: outer diameter minus inner diameter divided by 32. Okay. So from this equation, we can basically evaluate the shear stress induced due to the torsion, which is TR by J. If we put this equation and change it into the diameter, we get this pure torsion in the shaft, that is rho is equal to 16T by pi d cube. So as we in the previous section, we have seen that the section modulus, which is Z is equal to moment of inertia by the y max, which is from the neutral axis. So from this we get the section modulus. For the similarly for polar moment of inertia, we have polar modulus Zp, which is J by R. So from this equation we can get. So what does the Zp means? Zp is the polar moment of inertia. That means if there is more polar moment of inertia, if there is more polar modulus, then the more torque is required to induce shear stress in the shaft. Means if you have more Zp, the better the shaft strength. Okay. So maximum torque in the shaft can be how much is the maximum torque that a shaft can transmit? So to transmit the maximum torque, the shaft should have maximum shear strength. So the shear strength in the shaft can be calculated from the stress strain curve. So from this we get the yield strength. So from this yield strength we can actually find the maximum shear stress, which is the yield strength divided by 2. So from this we can calculate the maximum torque that the shaft can transmit, so which is also dependent on the polar modulus. So that's the formula for shaft power. Shaft power formula is 2 pi n T by 60. From this we can also calculate the torque transmitter, average torque value transmitter by the shaft. So next, what do you mean by axial rigidity? Axial rigidity is nothing but E times A, that is elasticity times the area. So for a given bar like this, or bar or beam, so if it is under tensile stress, so the tensile stress formula is this. From this we can basically evaluate the deformation, which is equal to PL by EA. So EA is basically the axial rigidity. That means if there is increase in the axial rigidity, then there will be less deformation. So if you want to compare what is the rigidity as well as what is stiffness, so from this spring system we can basically find that stiffness is nothing but the applied load per unit deformation. So K is equal to F by X. So from this expression we can compare it with here. So same expression, F by X is equal to K. So from this expression, P by delta X, that is the force time by per unit deformation, is EA by L. So this EA by L is the stiffness. So that means stiffness is nothing but the axial rigidity by per unit length. Okay. If from this expression we can basically come to a conclusion that if we say the bar is stiff, it means that the stiffness, if the stiffness increases, that means the length is less, the elasticity is more, the area is more. and in such case the deformation is less. So from this we can make basically the relations. Okay, next is what is flexural rigidity. Flexural rigidity is nothing but E times I, elasticity times moment of inertia. From this beam which is bent due to the shear force, from the moment equation we can basically evaluate the moment is equal to EI by R. So this is EI is the flexural rigidity. It means that if the flexural rigidity is high, that means the moment of inertia is very high. That means if the moment of inertia is high, that means the beam or the bar won't bend easily. Next one is the torsional rigidity, which is G times J, GJ. From the torsion equation, we can basically identify T is equal to GJ by L by theta. So GJ means if there is increase in GJ, that means there is high torsion. So to twist the shaft at the given theta angle, it will need GJ torsional rigidity to create such a torsion. So if GJ is high, that means torsion is high, and it will be much harder to twist the shaft at theta angle. So from the stress strain curve, we can basically estimate the rigidity, stiffness, and elasticity. But how? From the stress strain curve, from here, from this proportional limit, we can basically identify the elasticity, that static is equal to E. So from E, we get elasticity directly from the stress strain curve, but the rigidity and the stiffness we get it indirectly. So if we multiply E times A, we get the rigidity, and if we divide by L, we get the stiffness. It means if there is high elasticity, the rigidity is high, that as well as the stiffness is high. So next is from the stress strain curve, what do we mean by engineering or conventional stress, or engineering stress or engineering strain, or conventional stress or conventional strain? It is nothing but when the specimen is tested under universal testing machine UTM. At this time, the stress which is calculated as F by A and the strain as deformation by L, the area and the length is basically the original area and original length. It is not instantaneous length. While the true stress and strain is nothing but the area and length are taken instantaneously, and we can basically calculate the true stress and strain with this formula. Okay, so basically from this graph we can understand that here there is a strain hardening. Okay, that means due to the suddenly due to the elongation, the intermolecular forces becomes very high. It means the it takes a lot more stress to create deformation. So this is called hardening. But in the true sustain curve is higher. That's because it assumes that if there is a less area, means due to this necking area, the area is less, the stress is higher. So it's basically wrong. We only take the engineering stress and strain. Okay, because in this area the resistance force is high due to the intermolecular resistance force is high. Okay, so next from this stress strain curve for the mild steel, which has less than 0.3% of carbon inside it. So from this graph we can get the maximum information about the various properties of this material, because it shows good variations, but in other materials we won't find such variations. So from this curve, what all information we get is that yield point, yield stress. From this we can basically calculate the allowable stress, which is sigma y by factor of safety, and we can calculate the upper yield point, lower yield point. We only assume the lower yield point for our material, which is also the design stress. This is the proportionality limit till which the Hooke's law is applicable. This is the elastic limit. Till this point, the material will regain its original position, and this is the upper yield point, which is already in the plastic region. If we go to this point, we will have the permanent deformation as this, and till this proportionality limit, the strain is 0.12 percentage, and from till this proportional limit it is elastic region, and after this is a plastic region. Okay, so there is a sudden jump here. This is because of the intermolecular forces. After certain yield point, suddenly the material loses its strength, so that the intermolecular forces loses the bonds. So sudden losing in the bond creates such a sudden variation. After that, due to the increase in the intermolecular stiffening happens. It means the molecular gets twisted, and that means at that time the intermolecular forces are higher, the resistance force is high. In that case, the stress is also high. So this is called strain hardening. After that, necking happens. That's because of the at particular region the like the deformation happens a lot, not throughout the material. So due to that, the area reduces at that particular region, and at that particular region the elongation happens rapidly, and stress is also, with the less stress the elongation happens rapidly, so that region is called necking. Okay, so till this point we get the resilience. The area is called resilience. This is the modulus of resilience, and the whole body, the whole area is called modulus of toughness. So until this ultimate tensile strength, the deformation strain deformation percentage is 20%, till the fracture point is 25% of strain. Okay, so basically we can consider the material failure at this point. If the stress crosses this point, we say this material has failed, not this point, because we basically take the stress at this failure point as the proportionality limit. Okay, for designing purpose. So next is, what are the informations we get also from this strain curve are basically resilience, toughness, ductility, brittlity, malleability, elasticity, strength 3 points as we can see, but we can't analyze the hardness, cannot be found from this. So basically the modulus of resilience formula is this, modulus of toughness is formula is this, in which we add the yield strength and the ultimate strength. Okay. So next is how we calculate the brittlity, ductile, and from the stress curve. So for the brittle material, so the material breaks within the strain within less than 5%. Materials are glass, ceramic, and concrete, and this height is basically higher for the brittle materials. And for the strong materials or tough materials, the area is high. So for example, so you can see the toughness is high, the area is high. And for the ductile materials, the length is small, but the strain failure is more than 5%, and is failure point is far away from the yield strength. And this is for ductile materials, which is copper and aluminum. Okay, and for the we use offset material for the ductile material because it is very hard to find the yield strength for this diagram. So what we do is we take tangent from this point and we create an offset of 0.2%, and this cross section, this interaction is called the yield strength. So these are the diagrams for the plastic materials. Rubber, you see after some time the rubber becomes very stiff, so we can't create more deformations. And this is for mild steel. So this is for the ceramic brittle materials. You can see the height is high and it breaks within 0.5%, less than 5% thing. This is for the rubber, and this is for the aluminum. Okay, thank you.